Welcome. This is lecture number 4 of the class on advanced power plant design at Carnegie Mellon in the spring of 2014. I'm Nick Seifert, and in this set of lectures we're going to be introducing the concept of irreversibility and kinetics. In the previous lecture we looked at thermodynamics from the equilibrium point of view. Now we're going to be going into what's called non-equilibrium kinetics. This is where we actually look at how fast heat is transferred or reactions occur or fluid flows through, let's say, a heat exchanger. So what we were doing before was figuring out what would happen, let's say when we were looking at exergy. We were looking at what's the maximum amount of work that we could get out of a system if we allowed the process to occur really slowly. In this one, we're going to be asking the question, well, if we need a certain amount of, let's say, heat transferred, in a certain amount of time, and we have a certain temperature gradient, we're going to need to ask the question, well, what's the area of the heat exchanger that we need to be able to do that in a certain, to get that much flux for a given gradient. So that's what I'm calling kinetics here. Also goes by the terms non-equilibrium thermodynamics. So there's going to be a lot of different things that can diffuse, and so I'm just going to cover the main ones that you'll see at power plants. And kind of the first one that's probably the most obvious is thermal diffusion. And this is when we have thermal energy being transferred across temperature gradients. Right. The next one would be called chemical diffusion, sometimes also called mass diffusion. This is when you have molecules of a species diffusing against a concentration gradient. So this could be if you had some kind of membrane separation process, you'd have chemical diffusion through the membrane, and the flux would be proportional to the gradient in the species concentration. So similar to mass diffusion, very similar, and you can actually put it in the same. You can put it in the same terms. Is chemical reactions, where here the only difference is that you're not keeping the number of molecules fixed. You're allowing, let's say, hydrogen and oxygen combined in a water vapor, but still what you have is diffusion of species across gradients, because in one part of your reactor there might be hydrogen and oxygen, and on the other side there's water vapor. So one way you can think about chemical reactions is diffusion of species across gradients, where there's actually kind of sinks. The chemical reactions that basically acts as a sink. So that's one way to think about it. The next one is a little bit non-intuitive at first, but it's momentum diffusion, and that's what's happening when you have pressure gradients. When you require pressure gradients to overcome, let's say, friction or viscosity in a tube. Let's say your tube is your heat exchanger. You may need to actually supply a pressure gradient to overcome the viscosity. And the reason for that is you actually have something called momentum diffusion, and that's the fact that at the walls of the tube, the gas or liquid can't have any velocity, but in the center it's going to have a velocity, and because of that you actually have a gradient in the velocity, which is effectively a gradient in the momentum. But guess what? Things like diffusing against gradients. So what's happening is you have species diffusing against that velocity gradient. And as it's doing that, it's actually causing irreversibilities, which you need to overcome through pressure drops. Okay, the last one here, which we won't cover much in this course, as opposed to in a course where we're looking at fuel cells, and that is charge diffusion. And that is diffusion of charged species across gradients, either in voltage and or in concentration. So we're gonna be looking at what's called linear non-equilibrium thermodynamics. and that's when the gradients in the potential are small. So let me define what I mean by small. So a gradient in a potential is small when the change in the gradient is small compared to the value of the potential divided by the random thermal motion. So what that means is that if the size of the gradient, let's say for a heat exchanger, you have a temperature of T2 or T hot on one side and T cold on the other, and then you've got the distance between that. What we want to know is that distance between the two temperatures, is that large compared to the length scale at which energy is randomized, which is close to the mean free path of particles. So if this is a metal heat exchanger, so it's a stainless steel heat exchanger, then the collision time is on the order of distance between the molecules, which is extremely small. So in that case, we can say that the gradients of the potential are extremely small compared to the random thermal motion. And when you're in this linear non-equilibrium thermodynamics, there is analogies between pressure, voltage, temperature, and chemical potential. So these are the potentials, and in all cases you can write that the flux of whatever is being moved, the flux is proportional to a constant times the generalized force, where the generalized so the flux is the amount of something per time, right? It's the amount of what we'll find that moves when there is a gradient in a potential. So what I mean by generalized force is a gradient in a potential. So the flux is proportional to a constant times that gradient of a potential. The amount of irreversible entropy production is proportional to the flux times the force. So in this case of linear non-equilibrium thermodynamics, because we can relate the flux to the force linearly, we can find that the entropy production is either going to go like the flux squared, right, or the force squared. You can write it either way. This is why, if you remember from, let's say, freshman physics, and you're trying to calculate the amount of heat generated in a resistor, you could write it either as V squared over R or I squared times R, right? So that's the same thing. That's the same thing here, right? There's two ways of writing the amount of irreversible heat production, or hence an irreversible entropy generation. Okay, so let's look at this analogy, because we've got some electrical engineers, we've got some chemical engineers, and we've got some mechanical engineers in this course. So I want to go through the analogy, because you may be familiar with one of these, but in the linear non-equilibrium thermodynamics case, if you know one of these, then you can know how to deal with all the other ones. So I learned electrical circuits first, so that's probably the easiest one to think about and easiest one to draw out, where you have resistors and you have power supplies and all that. So let me go through that one first. And so in that case, you've got wires, you'll have voltage, power supplies are supplying a certain amount of voltage. You've got what's moving is charged species, and the flow rate is the current, which has units of amps. And when you're in a, if you have a wire, you have something called the current density, which is the amps per centimeter squared, where centimeter squared here is the cross-sectional area of the current of the wire. You got resistance, and the inverse of resistance is related to the electrical conductivity. And then you can also have basically a storage, which is related to the capacitance. And you can write something called the Ohm's law, And the microscopic form of Ohm's law states that the current density is equal to negative times the electrical conductivity times the gradient in the potential. So that's what I was saying before. When this is a case of Ohm's law is a case of linear non-equilibrium thermodynamics, and that is the case because the gradient in the potential is that's valid when the gradient in the potential is small compared to the distance that the electrons will collide with each other, which in this case is really, really small. Right? We're talking about orders in nanometers. So as long as we're talking about the gradient and the potential being on the order of centimeters or so, or millimeters, we're fine with linear non-equilibrium thermodynamics. So that's the first case. So the analogy in hydraulics is that where you have wires, you can just draw pipes. All right, a pipe can be drawn as just a wire. So here, pressure is the potential, and what can supply the pressure is a pump, and what's actually being moved is volumes of gas or volumes of liquid. And then you have something called a flow rate, which is the volumetric flow of gas or liquid. And here, velocity is basically the flux density. So as you saw in the other one, current density was amps per centimeter squared. Here, we're taking meters squared per second and divided by the cross-sectional area of the pipe. And what you'll get is some kind of velocity. And here, the equivalent to resistance is the viscosity of the fluid in the pipe, and the storage, like the capacitance, is meters squared. So like when you're doing circuits, you can always draw a capacitor. Well, you can do the same thing if you have pipes, then you have like tanks, right? So a tank is effectively like a capacitor in this analogy. And what matters is the storage. The equivalent of capacitance is the storage area. And you can get Poisson's law, which tells you the volumetric flow rate is going to be proportional to pi r to the fourth divided by 8 times the viscosity times the gradient in the pressure, right? So this is Poisson's equation is only valid when you're in the laminar flow region and there's small gradients in pressure. Okay, and the next one in the analogy is if you're using heat conduction, you have heat conductors. So this could be heat exchangers, or this could just be the glass that separates the glass in your windows that are separating your house from the outside environment. And here the potential is the temperature, and what supplies heat is, let's say, a heater or some kind of chemical reaction. And what's being moved is thermal energy, and if it's a solid material, that thermal energy is being transported by phonons. And so what's moving is the thermal energy in the phonons. So there's a heat transfer rate, which is the amount of energy in the phonons being moved, and you can always normalize that by the cross-sectional area of the heat conductor. So for like the glass window case, we're talking about the area of the glass window. If you calculate all the heat flux flowing through it, and then divided by the cross-sectional area, you get the heat flux. And the equivalent to resistance is 1 over the heat conductance, the thermal conductance. And here, the analogy to storage, as in the heat capacity, is the heat capacity. So that's that C sub P. If you have, in this course, we're not going to be all the capacitance storage area, or the heat capacity of a heat conductor is important when you have dynamics, which we're not going to be covering dynamics in this course, but I just wanted to point out that there is an analogy in all three of these cases. And then the microscopic form of heat conduction is called Fourier's law, which says that the heat flux is equal to negative times the thermal conductivity times the gradient in temperature. Okay, I've got this shown up one more time just to show that there's going to be one other case that we're going to look at, and that's diffusion, and the analogy also holds here. In this case, what we have, the potential is called the chemical potential, which is related to the conductivity, which is related to the concentration. And what's moving here is actually molecules. And so you have something like a diffusion rate, which would be moles per second. And once again, you have a cross-sectional area in which diffusion is taking place, like through, let's say, a membrane. You'd be calculating the moles per meter squared per second, where that's the meter squared, that's the cross-sectional area of the membrane. And here the analogy to conductivity is the viscosity, meaning the higher the viscosity, the more flux you get for a gradient in the concentration. In this case, you get something called Fick's law, which is that the diffusion flux is equal to the negative times the diffusivity times the gradient in the concentration with respect to x. I do want to point out that in general there is no fundamental one-to-one mapping between pressure, voltage, and temperature. It's just that it's useful to think this way, and it's valid when to use this analogy when you're in the linear non-equilibrium thermodynamics, i.e. small gradients in the potential. I do want to point out that these linear equations break down, and they break down in a couple different places. And they can break down when you have chemical reactions, because chemical reactions are often not close to equilibrium. And one way to think about this is, if you remember on the previous slides when we were talking about the partial pressure of hydrogen in the environment, and it was like 10 to the minus 40 or something like that, right? So when you have hydrogen and you're turning it into its concentration in the environment, you have something going from, let's say, 1 atmosphere of hydrogen to 10 to the minus 40 atmospheres, right? And that is a huge difference in concentration, especially when you're taking the log of it, 1 divided by 10 to the minus 40. So in this is one of the reasons why chemical reactions are often you can't use linear non-equilibrium thermodynamics to describe what's going on, is because they're often very far from equilibrium. Meaning within a few collisions you can have huge gradients in concentration when you have chemical reactions. Another place this breaks down is at shock fronts. And so that is one classic place where you cannot use any of these equations. Is at a shock front you have gradients changing, chemical compositions, you have temperatures and pressures changing within the collision, within a few collisions. So that's one place these equations won't work. Another place is that Poisson's equation is only valid for laminar flow, is not valid for turbulent flow. So that's another place where it can break down. So formation of eddies means that you have additional sources of irreversibility occurring. So I just mentioned the word irreversibility, and so far I haven't really explained what irreversibility is, other than in the coin analogy case I said it's when you turn silver dollars into quarters, quarters into dimes, dimes into nickels, nickels into pennies. But that's I do want to point out that there are cases where there are situations in which irreversibility doesn't happen, and I want to first talk about that before I go into really describing what irreversibility likely is. So there are some situations, and I encourage you to take a look at the link to the YouTube video. When you create superfluid helium, you create a situation in which you have a fluid that can move with no friction. And so if you go and check out the video, you can see you can run fountains forever without needing to continuously supply energy into the system. The fountain will just keep on running and running and running and running without irreversibility. So that's kind of interesting. Basically, there are ways you can get rid of friction, and superfluid helium is one of those. Another one is superconductivity. As you know, when you have a superconductor, you can have the flow of electricity without needing voltage gradients. It means you're essentially getting rid of friction by, in this case, cooling it down. And another place where you find that there is no reversibility is, let's say, lasers or photons traveling from the sun to the earth in a vacuum. When you have photons traveling, so you have a bunch of these photons, let's say in a laser, but they don't just randomly turn into photons of lower energy, right? It's not till the photon hits something like the earth, like when photons from the sun hit the earth, they eventually get turned into infrared radiation if they don't immediately get scattered. So it's kind of interesting to think, like, so why don't photons just, right, if the trend is in general for things to, the high energy photons to turn into low energy photons, when you're in a vacuum they don't, and superfluid helium doesn't seem to be irreversible, just keeps on going on, it keeps on going around, right? Or the Earth keeps on rotating around the sun, and if it was only those two species, two bodies, gravitationally, we don't see just those two. They could go around in circles or ellipses for a while. So it kind of begs the question, so what is irreversibility? So what I want to point out here is that there are four forces, in physics there are four known forces of nature. And it turns out only one of the four forces of nature is not time reflection symmetric. So the gravitational force, the electromagnetic force, and the strong nuclear force are all time reflection symmetric. Which means that there really is no way, if you're just looking at a picture, to tell whether something was going forward or backwards in time. But with the weak nuclear force, there is a way to know if something is going forward or backwards in time. It's actually, the force itself is not time reflection symmetric. It basically has a preference for one direction of time than another. And just as it also has, it's spatially asymmetric as well, like it has a directionality to it. So it's kind of interesting because it turns out that, right, we don't see irreversibility when we just look at gravity, and we don't see irreversibility when we just look at electromagnetism, right? When we just have photons traveling across through a vacuum, we don't see irreversibility occur. When we see irreversibility occur, happens to be when we see electrons colliding basically into other electrons, or protons colliding into other protons, or atoms colliding into each other, which have lots of electrons, right? But when two electrons are able to combine and turn into what's called a boson, so when two fermions can combine and turn into a boson, like in superfluid helium, we stop seeing irreversibility. So there's something about fermions that make irreversibility occur. And it turns out that the weak nuclear force only fermions feel the weak nuclear force, bosons don't. So what you have is the case that what is going on has something to do with the collisions between fermions such as electrons or those other fermions. But it's easiest to think about electrons, because when you have two atoms collide, you have the potential for a lot of electron interactions. So when they get really close to each other, they can interact via the weak nuclear force. When they're far away, all they could potentially interact with would be gravity or electromagnetism. But when they get really close, they could have the potential of interacting with the weak nuclear force, which effectively means that time reflection, that you could have an era of time when they can collide and interact with the weak nuclear force. So the way to think about this is that for our purposes, it's the outcomes of collisions are essentially probabilistic, and you lose information about the collision after after the collision. So there's no loss of information until they collide. So it's that irreversibility has something to do with collisions, and we can think of it the way that Ludwig Boltzmann thought about it was he made the assumption that there's something called molecular chaos. That means that once two particles collide, they lose information about where they came from. Right? That information would not be lost unless there was the weak nuclear force. Because just with gravity or electromagnetism, you don't get the loss of information about where they were before the collision. For that, you need something that's time reflection asymmetric, such as the weak nuclear force. So I want to point out here is that you can avoid irreversibility. So I said one way of doing it is doing things really slowly. The other thing is to set up the situation such there are no fermions. If you, like superfluid helium, if you can design, or superconductors, if you can design your system to be that not have fermions, you can basically have the system go around without friction forever. And but of course, right now those things are all really expensive. But the goal for superconductors is try to get the temperature at which superconductivity occurs to go to higher temperatures, so that we can be using this and have it cost less money. Okay, so let's step back and review. So I'm going to explain why this is important for power plants. So what we're going to find here is that irreversibility destroys the amount of work that you can do. However, attempts to try to minimize entropy production or irreversibility often increase capital costs. So one way of decreasing or increasing the amount of power from a power plant can often be to increase the size of heat exchangers. But what you find is then the capital cost goes up, and there's going to be some optimum between when you design heat exchangers, you'll find that there's actually an optimum area for heat exchanger, such that if you were to shrink the area of the heat exchanger, what you'd find is that your power production would start dropping. So your capital costs would drop, but your power production would drop, but such that your power production would drop more in equivalent terms than your power. And then if you were to increase the area of the heat exchanger, what you'd find is that the capital cost would increase more than your increase in your power production. So there's actually some optimal location, an optimal area. And it's important to know what causes entropy production and what doesn't. So for irreversibility to occur, and hence exergy destruction, requires both flux and gradients and potentials. So you could have flux of particles, but if there's no gradient and potential, let's say for a superconductor, right? You have flux of current, but there's no gradient and potential because there was no friction. There was no collisions between fermions in that case, right? And So irreversibility we can think of is loss of information about the system, because there's more permeations available. So in the coin analogy case, when we had silver dollars, if we had 10 silver dollars, it doesn't take much information to know a lot about the location, let's say, of those 10 coins. But as those coins start turning into pennies, so that we now have like 1,000 pennies, right? But if we only had 10, if we only started with 10 things of information, we lose, relatively speaking, we lose information about those pennies, is one way of thinking about it. We lose information about the exact state of the system. When everything was silver dollars, we had a lot more information about the system than we did when it's turned into pennies. So now what I want to do is I want to show an example so we can try to build some intuition on how irreversibility actually causes the amount of work you can get in a system to decrease. And this is going to be one of the main themes going forward throughout this course. So what I've put together an analogy here of water storage, and we've got water being stored in a tank 1, which is our reservoir, and then we have a frictional pipe connected to tank 2, and then at the bottom of tank 2 we've got a valve going to a water turbine, and then after the water turbine we've got tank 3, and then finally following tank 3 we have another pipe, and then the output of the pipe is a river at ground level here. So from the pipe the water has no height. From that last pipe there's no height. It can just flow out into the environment. So initially there is a difference in the height in tank 3 and tank 2, and it's a very sizable difference. And so this is called hydraulic head. The height is the hydraulic head, and from that you can calculate the work how much work you could hypothetically get out if you're flowing water if you could maintain that height difference. Right? And that would be related to how much energy was in the reservoir. So I also want to point out, you could also imagine in this this analogy isn't just for water. It's also, I use this sometimes when I teach in the fuel cell class. We can think tank 1 is a reservoir of hydrogen, and tank 2 is the anode of the fuel cell, and there's hydrogen at the anode, like right at the catalyst, where the actual electrode is. And then we have our open circuit potential between the anode, which is tank 2, and tank 3 is the cathode. And then we have a pipe going to the air side, and so we're flowing air, we'd be flowing air in this analogy if this was a fuel cell. And in air there is virtually zero hydrogen because it will oxidize with oxygen and make water vapor. Right? So think about this either as a reservoir of hydrogen, or think about this just as a water reservoir, and then in that case it's a turbine, water turbine. So we're going to start off, and you can see we have the potential to generate some work, but we're actually not generating any work yet in the turbine because the work is going to be equal to the flux times the gradient in the potential. So we're not getting any work yet. So we're going to actually allow the valve, and we're going to start opening up the valve and allow some flow through. Well, if we have pipes that are frictional, only so much water can get through the pipe at a given time. So what we'll find is that the level in tank 2 will start decreasing, and the level in tank 3 will start increasing because there's also friction on the other side of that pipe. So what's happening is you can think of frictional, the fact that things don't happen infinitely fast means that the actual height that we get, the height difference, is less than what it would be if things could actually happen infinitely fast. So friction and irreversibility end up causing us to get less work than we could have if we had had some kind of superconducting pipe that water could flow through without friction. Right? So, and then we could continue if we want to try to, there gets to be a point where we, there's going to be a maximum work that the turbine can actually output, and that happens when you start increasing the flow rate, it is compensated for an equal amount of decrease in the height of the potential. And at that point in time, you'll find you get almost like a, depending on what your system looks like, you can get like a, your work can look very parabolic, meaning there'll be a maximum. And then if you try to go even further, you'll find you'll get no actual work out of the turbine. So what I'm trying to point out here is the concept of exergy destruction. And that is because of irreversible processes, the capability to generate work, hence exergy, is destroyed. And exergy destruction turns out to be proportional to, is equal to the temperature of the environment times the internal generation of entropy within the system. So all of those irreversible processes, all those collisions and friction between fermions is destroying exergy. And that amount of exergy destruction is equal to T naught times sigma dot irreversible. Now, the thing I want to point out here is that, of course, the exergy is destroyed only with respect to the reference temperature of the environmental reference temperature. So here, when we talk about exergy destruction, one thing that could mean is that photons from the sun at 6,000 degrees Kelvin come here, and then we could they could turn into IR photons at a temperature of 300 Kelvin, and there'll be a large generation of exergy destruction. And because there was capability to do work with 6,000 degree photons, but 300 degree photons we can't do anything with here on Earth. Now, if we lived on someplace that was only 10 degrees Kelvin, then the exergy destruction of that process would be a lot less. Meaning, to somebody whose exergy destruction is relative to what you take as your reference environment. If you take the reference environment to be the cold of outer space, then the exergy destruction is virtually nil. Right, so that's one thing to keep in mind. Exergy is always with respect to what you take to be the reference environment. But that reference environment can in some ways is arbitrary. But in some ways it's not arbitrary. When you actually live on a planet and you can't get off that planet, then that reference environment is not arbitrary. And finally, in this, I want to give a breakdown of where exergy destruction occurs in a coal power plant. And I just want to give this because this is going to be, we're going to be seeing a lot more of these type of breakdowns where we show subsystems, and we'll be showing how much exergy is destroyed in each of the subsystems of a power plant. So here I just want to give you a feel for what's going on in a coal power plant where we're combusting coal and using that to boil and then superheat steam, and that's going to be going through a steam turbine. After the steam turbine, it's going to go to a condenser, so the steam turns into liquid water. It goes to a pump, and then from the pump it goes back into the heat exchanger where it's being boiled and then superheated. And in the condenser, there's also cooling water that's used on the other side of the condenser. Cooling water is used to remove the energy from the steam. So the two main sources of exergy destruction are first the combustion of the coal, and that can destroy about 30% of the inlet fuel, 30% of the exergy in the inlet coal, and then transferring that thermal energy from the flue gas, right, from the combusted coal gas, which is nitrogen, oxygen, carbon dioxide, and water vapor. When you transfer that energy to the steam, that destroys another 30% of the exergy originally in the coal. The steam turbine has only a small amount of exergy destruction, only about 3%. The condenser, there's certainly a lot of energy being transferred in the condenser, but only a very, very small amount of exergy is destroyed. Because thermal energy at low temperature has very low exergy. So there isn't much exergy destruction in the condenser, and there's virtually zero exergy destruction in the pump. The pump is just not consuming much power, and liquid pumps typically have very, very low exergy destruction, normalized to the exergy in the fuel. I want to point out the other sources. To get this to sum up to 100, you have to look at the fact that there's still some exergy in the flue gas as it leaves the stack, meaning as it's put out into the environment. There's still typically about 3% of the exergy. You could try to get some more energy out of that. So you could try to go after that exergy. Of course, to do so means putting a lot more and larger heat exchangers, and there's going to be a capital cost to doing so. And as we'll see later in the course, there's normally some kind of optimal in which you don't want to leave too much energy in the stack gas, or else you could still be getting more power from your power plant. But if you go to the other extreme, if you try to get every single last drop of exergy out, the size of your heat exchangers start becoming enormous, and then your capital cost gets really high. So when you end up optimizing for the return on investment, you find there's going to be some optimal in the middle, where you allow some gas to leave, but you don't let all of it. You don't want to have huge exergy remaining in your stack gas. And then the last thing I want to talk about is there's cooling water that is flowing on the other side of the steam condenser. And that cooling water, it has a lot of thermal energy, but as you can imagine, because cooling water is only going to be maybe 10 to 20 degrees above room temperature, there isn't much exergy, even though it can be carrying away sometimes up to half of the original enthalpy that was in the coal. It's only carrying away perhaps 2% of the exergy that was originally in the coal.